Welcome back to 4.2, the change of variables and Jacobian. So far we've been dealing with rectangular regions. Today that will still be the case, but we will shift space a little. So what do I mean by shift space? Well, the Jacobian is a determinant of a matrix that determines the multiplier for each area of each grid square in the Cartesian plane. So this matrix that the Jacobian determines shapeshifts the grid, and the Jacobian would calculate the area of the new grid square. So what does that mean? Well, if we have an x coordinate like this and a y coordinate like this, an x and a y like this, and we turn it 45 degrees and we make it a little bigger, it will turn like this. This will be the new x-axis, or the new x direction, and the new y direction. So to illustrate it better, we'll go to the next slide. So this is the x direction, right? This is a grid, just the xy plane. Let's say this is the xy plane, right? And then this is the new grid. This would be called, I would usually call it the UV plane. The UV plane. Um, and that's what I will usually call my variables, u and v. So what is happening? Well, this is the original matrix. This is the first unit vector basis, 1, 0, I unit basis vector, which goes in the x direction. J unit basis vector goes in the y direction, 0, 1. That's the second vector. Now, you don't usually see vectors written like this. You usually see them written like this, 1, 0, and then 0, 1. But that's just another way people write vectors. When people write it with x, y like this, then you will be able to observe that it's simply just going to be x and y. So that's why it's normal. That's why it's called the original matrix. That's why it's called the Cartesian plane, and that's why we made it to be like that, because it's simple. Now, if we multiply this with x, y, which is supposed to be our new basis vectors, we will get the u dimension. So we will get the fact that the u dimension is x plus y, and the v dimension right here is negative x plus y. Or I'm sorry, that's wrong. That's wrong. Okay. Okay, for this vector, you will end up with something completely different. So here's the basis vector v1, 1 and negative 1 right here. It's pointing down. And then the basis vector v2 is pointing up, right? Or up to the right and down to the right, which is totally different from this one. So yes, this is what happens. The matrix shape shifts. It shifts the vector, or it shifts the Cartesian plane so that it looks still like grid squares, but it looks a lot different. And in fact, there will be some instances where it looks a lot different than grid squares, like what we're about to do in a second. So what does this mean? How does it affect the area under the curve if it's like this? Or the volume under the surface if it's like this? So if dA is equal to dx and dy, and we have u is equal to x minus y, like this, and v is equal to x plus y, like this, then our dA will be equal to, I think I actually got this wrong, so let me just fix it real quick. Du dy, or du dv, or I'm going to name this dA2, is equal to du dv. So our du dv vector right here, or our du dv coordinate plane, uv coordinate plane, is this many times, whatever this determinant is, many times bigger than dx dy. So what is this determinant? It's 2. If you did cross products, you will be able to figure out what I'm doing with this. It's basically just the minor matrix rather than the entire 3x3. You're just doing the 2x2 part. So it's du dv is equal to 2 dx dy. that means one of these squares are worth 2 more than this square. Which makes sense, because this is bigger than this square, right? So how do we write this? We actually write du dv is equal to the determinant of the Jacobian, which is written like this: u comma v x comma y dx dy. Right? And what does this mean? What does this symbol mean? That brings me to the formal Jacobian, actually. So the formal Jacobian is this: if this is equal to this. So what does this mean? What does del u comma or partial u comma v over partial x comma y means? It means a matrix of partial derivatives. U sub x, u sub x, v sub x, u sub y. I think I did it wrong. No, I didn't do it wrong. Okay, u sub x, u sub y, v sub x, v sub y. I think and that is what the matrix means. So how does that work? How does that work? Let's say u is 3x plus y, and then v is negative 2x squared plus sine y. So you will have the Jacobian u v over x y is equal to what? Is equal to 3, 1, negative 4x cosine y. So then you would have your determinant is equal to the determinant of this thing, which is equal to 3 cosine y plus 4x. So it's a little bit wild. And usually we would actually want to convert these y's and x's in terms of u's and v's, but we're just doing very simple Jacobian stuff right now, so u and v usually isn't this complicated. So now this only works if it's du dv if we're having u is equal to a function of xy, and then v is equal to another function of xy, then we can use this. However, let's use teal. However, if we have another situation where x is a function of u and v, and y is a function of u and v, then we cannot use this. We would actually have to say that dx dy is equal to this instead: xy u v du dv. So it's a switcheroo, right? So what does this mean? This means it's equal to, instead of u sub x, it's x sub u, x sub v, y sub u, y sub v du dv. Right? So it's a switcheroo. It's a little bit strange. And I will help you notice. Sometimes you can just notice by kind of intuition. But I will help you notice which one you have to use, this one or this one, right? And it will make more sense if the numbers that you are working with are huge. But if the numbers that you are working with is like x equal to 1/2 u plus 1/3 v, and y is equal to negative u plus 1/6 v, then chances are you're gonna get a reduction in area. your area is not going to be as large just because these numbers are so dirty. All right. So from that, aside from that, we will use we will use these principles to calculate the change of variables. We'll use these change of variables to calculate this integral with the bounds or with the rectangle in u and v coordinates, this and this. If they're in x and y, it's gonna get really messy. I don't want to deal with that. So I'll let you figure out how you can substitute u and v into this equation right here. How can you substitute it out? In fact, I kind of already pointed it. So I'll give you 3, 2, 1, and this is how you will be able to substitute it. Notice 2x minus y is right there, so you can just put v, and then x squared plus 2xy plus y squared is x plus y all squared. So it's u squared. So yeah, that's it. That's it. Or is it? Is that it? No, it's not. That's not it. Why? Because we got to take into account the Jacobian as well. So how do we participate, or how do we calculate Jacobian? Well, du dv is equal to, so this is in dx dy right now. This is dx dy land. Why? Because there's x's and y's here. So du dv is equal to partial u v over partial x y dx dy, which is equal to u sub x 1, u sub y 1, v sub x 2, v sub y negative 1. So it's negative 1 minus 2. Negative 1 minus 2 is negative 3. But it can't be negative since it's a determinant, right? Determinants, actually, that is a complete lie. Determinants can be negative. So dx dy, even though there's a two like absolute value bars, determinants can be negative. It's a little bit weird. But I made a mistake. I did think about for thinking that it can't be negative. It can be negative. Negative 3 dx dy. So since this is a constant, it's very easy. We can just take it out of the integral. So what will happen is we'll have negative 3 times the double integral from 0 to 1. I'm going to go 2 to 5. Even though 0 is the easiest first, I'm just going to go and do it last. And then I'll do dv first and du. These are the v coordinates. These are the u coordinates. So what will that give us? That will give us negative 3 from 0 to 1 of u squared v plus v squared over 2, and from 2 to 5 du. So let me shrink this a little bit. Okay, it gets really disgusting. Alright, so let's just shrink this. Let's shrink this. Let's put it up here, and let's continue. Alright, so what is this? This is 5u squared plus 25 over 2 minus 2u squared plus, or I should put u, in order to be a little bit more clear, v equals 2, v equals 5. 2u squared plus 4. No, 4 over 2, so 2. So what does this mean? This is 3u squared plus 21 over 2. So then now, this is the double integral, or the single integral, not double. Negative 3 times the single integral of 3u squared plus 21 over 2 du. Or I'm sorry, it's not 3u squared, it's just u squared. No, it is 3u squared. I'm stupid. I worked it out right down here. Negative 3 from 0 to 1 of u cubed plus, of u cubed plus 21 over 2u from 0 to 1, which is negative 3 times 23 over 2, because 0 will give you nothing, and then negative 69 over 2. And that is your area under the curve for that region. And I'm starting to think that I might have done it wrong, because this is a very, very, very weird predicament where we have negative area, but I think this is actually very, very positive. I hope I did it right. If it's not right, I'll fix it in the comments. But anyways, we're gonna continue because alright. So the next section is find the area of two-dimensional rectangle, two-dimensional shapes. You can actually use the same method just to find areas of two-dimensional shapes. Ones that we would just use one integral usually, but now we can use two to do it. How is that any special? Well, we don't have to rely on a function, is how it's special. So find the area of the rectangle -2, 3, 1, 4. So what will that look like? That will look like -2, 3, 1, 4. So something like this. It should be 15, right? Because that's 5 and that's 3. So let's check it out. So how's this gonna work? I already hinted to it. We don't need a function. This is how it's gonna work. Literally, we don't need a function. So this is equal to what? It's equal to -2. I'm gonna put dy first. So -2 to 3, 1 to 4, dy dx. So why does it work? Well, if you're thinking about it, 1 to 4 dy, we're adding all of the y's from 1 to 4. We're just adding all of the y's from 1 to 4. So this will be like small dy's right here. Right? dy. So we're adding all of these dy's from 1 to 4. And then that will give us an entire line after this first integral. So this first integral will give us the line. And then if you multiply that by a little bit of dx, that will give us the area of this little slitter right here. So we're just summing up all of the lengths anyways. So this is the integral that we've already worked out times dx. So what's the integral of 1 to 4 dy? Well, it gives us the whole line. So what's that times dx? Times dx. It's a small slither. So what if we sum all of those dx's from -2 to 3? It gives us the area of the entire rectangle. So what is the area of this rectangle? Well, let's work out a double integral like how we would work out usually. So this is -2 to 3 of y from 1 to 4 dx, which is -2 to 3 of 4 minus 1, 3 dx, which is equal to 3x from -2 to 3, which is equal to 9 minus -6, which is 15. So yes, it works. So the area of a two-dimensional shape can just be expressed as the double integral of a region D dA with no function in the inside. So let's find the area of the circle r equals. In order to find this area of the circle right here, we need to find a Jacobian, right? Because that's what the entire lesson is planned about. So what is the Jacobian for this circle? Well, if we have r equals 5 like this, I wouldn't want it to convert back to x and y. So I'm just going to dish out the polar coordinates. X equals r cosine theta, y equals r sine theta, and then we can work out the Jacobians. X sub r is cosine theta, x sub theta is -r sine theta, y sub r is sine theta, and y sub theta is mind blank, r cosine theta. Alright, so our Jacobian x sub r, x sub theta, y sub r, y sub theta is r cosine squared theta minus -r sine squared theta, which is what? Which is just r. It's just r. So that what does that mean? That means that dx dy is r dr d theta. So now with this knowledge, we can integrate. So let's start integrating. So what's this circle? How do you find the area of a circle? With how does polar integration work? First of all, polar integration works on the small dr slivers that you get. These are small dr slither that you get, and then when you add all of your drs, let's say from 0 to 5, it would be something like this. So that is 0 to 5 dr. And then if you add a little bit more, this length right here is rd theta. So times rd theta. And then you will get this pizza slice. You will not get a rectangular region. You will get a pizza slice. If I can draw it right. There you go. It's very, very small, kind of scuffed. Just a very small highlight. Just to highlight this region right here. There you go. So that is the region that you get when you multiply 0 to 5 dr, basically the radius, times the little slither rd theta. So the integral will be double integral, or the iterated integral, from 0 to 5 dr, or rdr, or from 0 to 5 rdr d theta, and then d theta will run from here all the way. So what is all the way? Is 0 to 2 pi. So what will this give us? This will give us, well, the integral of r dr is r squared over 2 from 0 to 5, which is what? 25 over 2. So I'm going to put down all of the 0 to 2 pi stuff as well. So let's make this even smaller. Let's shift this to the, oh gosh, let's shift this to the right here. And what does this mean? This is equal to 0 to 2 pi of 25 over 2 d theta, which is simply just a multiplication. This is 25 pi, and if you calculate this, just circle in general with pi r squared, you will get the exact same answer, 25 pi. So if you use a dummy variable, you can actually just work out the area formula. It's pretty good, pretty cool. So this is 25 pi. Example: a washer has a non-uniform density of delta xy is equal to 1 over x squared plus y squared. So find the mass of the washer if its inner radius is 3 and outer radius is 5. So we've been thinking of these double integrals with f of xy in the center as volumes, but we can also think of it as masses. Or we can also think of it as a calculation for a mass if f of xy in the center is a density function. Why? Because we're adding all of the small contributions to masses that each density we're integrating is contributing. So if you have like a slice of pizza, or a slice where this part is way more, like way less dense than this part, then you could add the little contributions dm, which is equal to r, we could add the small contributions dm, right, which is equal to probably something like r times d density, r times the small change in density, or density times the small change in dr. Right, so the density function times a small change in dr is equal to your small change in mass. And if you add up all of the changes in mass, you will get the mass of the entire thing. So let's draw the picture. Inner radius 3, not a very, actually quite an okay circle. And then outer radius 5. So let's say something like that. That was pretty okay circles. I expected way worse. So that's 3. Use a different color. That's 3. And that's 5. The entire thing's 5. There you go. So how does this work? Well, the double integral dA, this section is the area. You have to know that. That section is the area of the washer. But we want to find the mass. So we want to add x something extra. We have to add the density function in the middle. Because in real physics or in real life, density per unit area, density is equal to area divided by, no, not area, mass, m, I'm just gonna say m, divided by area. So area times the density is equal to mass. So this is what we're doing right here. This is the area. This is the density. I'm just gonna say x, y. That's the density. And then we get mass as a product, right? So we're timesing the area by the density is basically what I'm saying. So density x, y, dA. So because it's a circle like this, our bounds are pretty easy. Our bounds are 0 to 2 pi for theta, because we're integrating the entire circle. We're having the slices over the entire circle. The radius is 3 to 5, since we only want to count the mass starting from 3 and ending at 5, since that's what the range of our washer is. So, or the domain of our washer is. So d r RD theta is our Jacobian. And this is 1 over x squared plus y squared. X squared plus y squared can be substituted for r squared. So 1 over r squared dr d theta. So what will this give us? This will give us, that's equal to the integral from 0 to 2 pi of negative 1 over r, no, that's wrong. R times 1 over r squared is 1 over r dr d theta. Still 3 to 5. So what will this give us? This will give us the integral from 0 to 2 pi of the integral of 1 over r is not negative 1 over r squared, is ln r from 3 to 5 d theta, which is equal to the integral from 0 to 2 pi of ln 5 minus ln 3 d theta, which is equal to 2 pi times ln 5 minus ln 3. And that is your mass. That is the mass of the washer. That is how, it's not how much it weighs, it's the mass, is the amount of stuff in the washer. It's 2 pi times the natural log of 5 over 3. And that is approximately, I'd say, like 8 or 10. 8 or 10, I think. I don't know what the exact amount is. Actually, no, it's probably like 5, about 5 kilograms. Pretty interesting washer. The washer gets more and more dense as you get to the center, and that's why we're not integrating from the center, because if we integrated from the center, it might actually be infinite mass, and that would be pretty problematic for this type of question. The density function's undefined for the center, so it could be infinite. It literally could be infinite, which is not what we want. So that's why we did this with a more sensible domain of r equals 3 to r equals 5. So that's it, I think. Yes, that's it. I will see you next time for integrating over non-rectangular regions and non-circular regions.